Swayam Prabha. Digital India. Educated India.
Welcome back, students. In the previous lecture, we finished a few circuits using PN junction diodes. Now I would like to introduce you to a new device called bipolar junction transistor. Now the PN junction diode by itself is kind of interesting because there are only two terminals and the current flows only in one direction depending upon the biasing. So it looks like a gate or the gate or a valve that opens only in one direction. Now what we really want is we want a third terminal which is like a control terminal. So using that control terminal we can control the flow of the current between two terminals. So obviously we need three terminal device, and there comes the bipolar junction transistor. Before BJTs in semiconductors came into play, there were vacuum tubes. I still remember I had an old-fashioned radio using vacuum tubes. And vacuum tubes, there is the same action that I'm going to describe to you about bipolar junction transistor. A similar action happens over there. There is a filament, tungsten filament, which heats up and it starts emitting electrons. And then there is a positively charged plate. And in between there is a control electrode, and by changing the potential on the control electrode, you can control the flow of current between plate and the filament electrode. So we can see similarities between vacuum tubes and BJT in terms of operation. In terms of vacuum tubes, the vacuum tubes are bulky, they were made out of glass, they look beautiful. If you open up an old radio and see the real vacuum tubes working, they all light up. However, they are not practical for integration because each BJT transistor can be like a bulky vacuum tube with glass and things like that. BJTs were invented in 1947 at Bell Labs by Shockley, Bardeen and Brattain. They got Nobel Prize in 1956 for their invention. Since then, till about mid-70s, BJTs really reigned the semiconductor space. BJTs propelled the miniaturization of electronic circuits. They were one of the key ingredients in explosive growth of integrated circuits. Of course, 1975, around that time frame, metal oxide semiconductor transistors, MOSFET transistors came into play and the scenario changed a little bit. However, BJTs are still revered for high frequency designs because they can offer excellent frequency response. They can offer operation in gigahertz range very easily. Bipolar junction transistor is a peculiar combination of two PN junction diodes. So let's draw the two separate diodes first. Here is your first N-P junction. And this we are going to, as N is negative, that's cathode, and P is positive, so that's anode, as I have shown you how to draw them. And there is another diode, which is a PN junction diode, except the sign is reversed here, PN. And the diode here looks like this. Now we are kind of merging these two P regions and we make this NPN transistor. So let's redraw the combo sandwich, and it looks like this. You have N, and you have P, and you have N. So the one region on the bottom, we're going to call that emitter. One in the middle, we call it base, and the third one on the top, we call it collector. The emitter has the highest doping, heavy doping. Then next base region, P has light doping, and the collector region is the lightest doping. So when we talk about heavy, light and lightest, heavy doping is generally shown as N+, light doping just P, and lightest doping is N-. All these represent the NAs and NDs for each type of impurities. And the symbol for the bipolar junction transistor is drawn like this. and I'm going to go through this in detail. This is your collector, emitter, and base. This is your NPN BJT or bipolar junction transistor. Let's look at how this BJT transistor is actually manufactured, and that will give us a lot of insights about its operation. So, top view of the bipolar junction transistor. So we will start with collector region, which is in blue. Collector region has N minus, lightest doping. Inside that collector region, then we dope with P impurity. So the doping concentration of collector N minus, this is our collector, is lightest, and the next one would be, this would be stronger doping compared to the collector. So since this is N minus, we would be doping it with phosphorus. So the ND for the collector would be small compared to the NA of the base region. Next one, we would have emitter region, which is the heaviest doping. This would be N plus. So in the N plus, which would be ND emitter, will be the highest. Impurities would be highest here for the emitter region. Okay, so this is the way a bipolar transistor is created. Let's do a cross section of this device, and that will give us a lot of insights. So I'm going to chop this transistor right here and then show you how the layers look like in the vertical dimension. This is a top view. So first we will draw our blue. This is the collector region, which is N minus impurity. Then we would have base region, which is shown like this, P impurity, and then comes the emitter region, which has the heaviest doping. Interesting part here that I would like you to pay attention to is the following. This is N plus, and to make metal connections, I'm going to use a different color so you can easily identify. So this would be the connection for emitter, and then we would have another metal connection here and another metal connection here. We will just do simple connections right now so that we understand how the device works. So these are all, the magenta colors are all metal contacts. The key point I would like to make here is width of the base region. So if you look here, the layer of P, which acts as a base region, is very thin. It's like a sliver, and we will see significance of this in the analysis of the bipolar junction transistor. There are three modes of operation for the bipolar. So I'm going to illustrate them, and then we will get inside the transistor how the carrier transport happens inside the bipolar. But before that, let's just look at the bipolar junction transistor at a high level, and then we will dig inside deeper. If you look at the device as we drew earlier, the NPN device, and intentionally shown in this way to understand the three regions: collector, base, and emitter. And I'm going to draw three columns here to understand the three regions of operation. So the first region of operation, which is the case when both base emitter junction and base collector junction, both are reverse biased. And this one is also reverse biased region. What this means is the potential we apply between base to emitter is such that the bottom diode is reverse bias as well as the top diode is reverse bias. So in that case, we call this a cutoff region of operation. In the next one, we would turn on the base emitter junction only. So base emitter junction is forward biased and base collector junction is still reverse biased, and we call that region active region. And as you would have guessed it, the last region of operation is where both the diodes are forward biased. This one is also forward biased, and this region of operation is called saturation region. Out of these three regions, the active region is the most used or most useful mode of operation for a bipolar transistor. So this is where you would be using for amplification, active region. And we will go into how that works. We will also look at other modes of operation. Now here I have drawn for you the symbol for NPN. It looks like this. So this is collector, base and emitter junction. Let's draw same thing for complementary device, which is PNP transistor, and that would look like this. PNP. So here is your PN and then NP junction. In this case, this would be the collector, this would be the base, and the last terminal would be the emitter. The PNP transistor symbol is collector, base and emitter. The flow of the current is shown in this way. Okay, the arrow is reversed, and we will play with some circuits using PNP also as we go along. To understand operation of BJT in active region, which is the most used mode of operation, let's start off with this part, which is the base emitter junction of the bipolar transistor. The PN junction is forward biased. So let's draw that forward biased PN junction diode. I'm going to exaggerate things a little bit to make a point. This is our P, and this is your heavily doped N plus region, which is called emitter. Now this is the junction region, and we have forward biased the base emitter junction. So this is base and this is emitter. So P should be positive, so we'll connect the battery here, and then N should be negative. It's important that you convince yourself first that this is forward biased. So this one we will call it VBE, positive. I would like to draw some graphs on this particular picture so that we can intuitively understand how this is working. Let's say that there are two axes here, which I'm going to show. One is this distance axis, let's call that X, going in that direction, and horizontally I'm going to draw doping concentration or the carrier concentration. So once we forward bias the PN junction diode, note this is a N plus region. What does N plus region mean? That means you have a ND which is very high compared to NA over here. So this has acceptor impurities and this has donor impurities. So emitter region is heavily doped, N plus region, so ND is very high, okay, compared to NA. So we would expect electrons, there should be a lot of electrons in this emitter region, and there should be relatively less electrons, which are the minority carriers, in the P region. So we expect diffusion to start happening. Okay, so there will be diffusion of minority carriers, which is the electrons, happening in the base region. So we can draw the profile. Let's assume that the left side of this horizontal axis is high Okay, and the right side is, let's say, some low number. That is just to show you the carrier concentration. As I said, we will have electrons diffusing from N plus region into P region, and we would see a carrier profile that looks like this. Similarly, there will be holes. The majority carriers in the P region, the base region, will also diffuse into the emitter region. However, since P is, and this would be our holes diffusing over here. Okay, so these are, let me draw here, this is electrons injected from emitter in base region, and this would be holes injected from base. So this has lower concentration and this has very large concentration, N plus. So there will be two currents, obviously. There will be a diffusion of minority carrier, which is electrons in the base region. So this would be your diffusion of electrons, which would be large, and you would have diffusion of holes also in the N plus region. So this would be relatively small contribution for holes, and that is happening because of N plus P, the heavy doping of the N plus region. Okay, now we will write equation for the current. The current equation I is, we can say that is dominated by the electrons in the base region because heavy concentration of N plus, and that would be Is exponential V base to emitter region by Vt. Okay, so if we increase the base to emitter forward biasing, then the current which is flowing, how is the current flowing? The electrons are dominatingly flowing in this direction, so the current is going to flow in the downward direction here. So follow this current flowing in this fashion. In the previous lecture, we talked about this current Is as just I just gave you an expression, but I would like to give you some insight in this lecture. This Is is actually, this Is is depends on this carrier profile that we are going to see. Okay, so Is is given by, first of all, is charge Q is proportional to the area of the junction. Okay, and then Is is also proportional to the slope of this curve. The steeper the slope, more is the diffusion, right? So the slope of the curve is d ends of P divided by dx, x being this vertical direction right here. Okay, and multiplied by dn, which is diffusivity. In this particular case, we are only looking at this for the electrons in the P region, because you will have similar expression for holes that due to dominant N plus diffusion, we are going to ignore that part. Okay, so let's see what these numbers turn out to be. So I'm going to just write more details. Q, area of the junction. What is D ends of P? What is the concentration here going to be? The concentration there is going to be Ni square divided by ends of A, acceptor concentration. Okay, so all that's a maximum concentration there. And what is dx? So dx is depends on the profile of this curve that we are seeing, the yellow curve we are seeing, and we use a constant called diffusion length, L's of n. N indicates electrons, diffusion length of electrons, and this ln is indicating how this curve looks like. If ln is small, this exponential decay that we are seeing in this yellow carrier concentration that is characterized by the diffusion length L. And in this particular case is the diffusion length of electrons in the base region. So other insight there is if Ln is small, then you can see this exponential decay would be faster, which means that the electrons are recombining faster. So Ln indicates kind of diffusion length within which the electrons are disappearing, they're recombining. Okay. Dn is a diffusion constant of electrons in p region. So diffusion constant numbers for your or diffusivity, Dn is kind of, I'm just giving you ballpark numbers here, 35 centimeters square per second, and d of p, which is for holes, the diffusivity is 12 centimeters square per second. Okay. So this is the expression for Is. In the previous lecture, we just used it as a formula, but I just wanted to give a little bit more insight into what's really going on. And specifically this exponential decay that we are seeing of the carriers in the lightly doped region. We would like to add the third electrode, which is the collector, and see how things change. This profile changes when we add collector, the third electrode collector. So adding collector, if you remember, we said it's a active region. In the active region, base collector junction is reverse bias and base emitter is forward bias. We already looked at that. So we will keep this as it is and we will only introduce the base to collector reverse bias junction. Now, key thing I would like you to remember when we did the profile of the transistor is the thickness of the base is like a sliver. It's so thin. Okay, so that is important part in understanding the bipolar transistor action. Okay, we'll keep that in mind when we are drawing. So we have N plus region here, which is emitter. Then we have P region, lightly doped compared to the emitter region. And the third thing we have is a N minus region, which is the collector region. Okay. And let's draw the picture, complete the picture. So here this was forward biased, positive and negative. This way. So this is plus minus VBE, and you can see it's forward biased. The N minus P junction, which is collector base junction, that is reverse biased. So we will put another battery here, something like this. So this would be our VCB, and that is reverse bias. You should be able to see this is positive and this is negative. So the base collector junction is reverse bias. All right. And as I said again, the base region is ultra thin by design. Since collector base junction is reverse biased, what happens between the collector base junction? I would like you to remember that if it's reverse bias, then what do we have at the junction? There is a depletion region. And what does depletion by definition means? There are no carriers. So what we will see is, I'm going to draw this really tiny depletion region here, exaggerated at the, like this. So that would be our depletion region. Okay. I'm also going to show you, this would be the width of the base region. Earlier, if you remember, when we just had the base emitter junction, we had this nice exponential decay of the carriers. And we said that then the current is going to flow this way of the electrons, right? However, as soon as we brought in the reverse bias p-n junction, what happens is the carrier concentration will go to 0 at that at that interface, and this yellow curve will morph into, it's going to look like this. It will go to 0. As I said, if you look at the axis here, this is high and this is 0. So by bringing in a reverse bias collector based junction, we have suddenly increased the slope of this carrier concentration. Let me erase this part. These electrons which are in the base region, they come close to the depletion region and they are attracted by the positive potential at the collector. And all this current, large current, which is happening due to diffusion of electrons into the lightly doped base region, it will straight away shoot through and it will flow to the collector. So the electrons which we were showing, now the current flow has increased. These are electrons. It will cross the boundary and it will flow through to the collector, as a result of which the flow of electrons is going to be in this direction and the flow of current is going to be in this direction. So this would be your IC, current IC flowing. Think about it this way. In the base region, we are kind of enticing the electrons from N plus region to come to the base region. As soon as they come into the base region, they are enticed even further by positive potential, which is at the collector. So some of them will flow through to the base due to recombination activity. However, most of them will end up getting attracted to the even higher positive potential at the collector. Okay? And that's how the magic happens. This is again an intuitive way of understanding the bipolar action, transistor action. Okay? Now let's come back to some numbers here. The steep profile that now we have, earlier we had an exponential profile. Now instead we have this almost linear steep profile. So what is the slope of that profile here? The yellow profile right here, the slope is going to be equal to d ends of p divided by dx, which is part of our current, and that is going to look like ends of po divided by width w. So important observation is we have current due to forward biasing of base to emitter junction, and that same current, the exponential dependent current on VBE, is going to flow through to the collector. That is the important observation. So in this particular case, we're going to say collector current IC is given by IS exponential VBE divided by VT. And this IS, as we talked about earlier, that is given by Q area and then d ends of p divided by dx, that's the slope of the curve, times the diffusion constant dn. Okay, this is your IS, which is equal to again Q area. What is d ends of p? That is going to be Ni square divided by ends of A, which is the doping in the base region, the holes doping in the base region, and Ni square divided by Na will give you the electrons concentration in the base region. And all this concentration is going to, you will have a slope or a gradient, concentration gradient in the base region going from Ni square divided by Na to 0 in the width of W. So that's our slope of the curve. Okay. Multiply that by diffusivity or diffusion constant of electrons in the base region. So we can rewrite this expression again. IC is equal to Q. Now I'm going to just write this as Q area of emitter. If you remember the three-dimensional picture, the emitter was inside, base was outside. So it's the area of the emitter, this area. That is what is important, area of the emitter. Multiply that by Ni square divided by ends of A and width of the base multiplied by diffusion constant N and exponential of VBE by VT. So the collector current IC is dependent on base to emitter junction forward bias. Okay, so that's the main observation. Other observations are kind of obvious. Collector current is proportional to the area of the emitter. Collector current is inversely proportional to the width of the emitter, and also it's inversely proportional to base carrier concentration. So lighter base doping would give you higher collector current. Let's talk about, we only talked about collector current now. There are two other pieces of carrier transport happening. One is in the base region and in the emitter region. One is there is a diffusion of holes in the emitter. So let's write down over here, holes diffusing in emitter. Let's call that IB1. That's the base current. So just like our electron profile, you will have a carrier profile here in the emitter region, although it will be small because this is N plus. Right? So as a result of diffusion, you will have base current IB1, and that is proportional to VB exponential VBE by VT. The second action that's going on is in the base region, we already have holes and they are recombining with some of the electrons. So holes recombining with electrons in base region, and that is IB2, base current contribution 2, and that is given by exponential VBE divided by VT is proportional to, again in a similar fashion. So total base current is given by IB is the base current is given by IB1 plus IB2. So generally we denote the base current as small fraction because all this stuff that's happening is really tiny. So the base current is a small fraction of collector current, IC divided by beta. The beta is in the range of 50 to 200 depending upon the quality of the transistor. Okay. Now let's look at intuitively what this beta really means. If the width of the base region goes down, then beta would go up because IC will go up. Also, if the emitter concentration and hole concentration in the base region, so this is emitter and this is base region Na, if we increase this ratio, then also beta will go up. Okay, so this basically tells you how heavily doped the emitter is. It's relative Nd divided by Na. What about emitter current? So we have looked at this. Now when we are drawing it this way, it should be obvious. So we know what collector current is, IC, and we know what base current is. Base current is given by IC divided by beta. So the emitter current has to be, Kirchhoff's current law is going to be IC plus IB. IE is equal to IC plus IB, which is equal to IC plus IC divided by beta, and that will become beta plus 1 divided by beta, and that would be IC. And this term beta divided by beta plus 1 is defined as alpha. Okay, so emitter current is then given as by collector current divided by alpha. Alpha is obviously less than 1. Okay, then we can write this expression as Is divided by alpha exponential VBE divided by Vt. So refreshing again, beta is called current gain and is generally very high, and alpha is very close to 1. If beta is high, then beta divided by beta plus 1 should be less than 1 but pretty close to 1.